Today we'll be talking about the Single Shot Multibox Detector for aircraft identification. So the military likes to use image data for a wide variety of intelligence applications. Here we're just going to focus on detecting enemy aircraft in the air. A main requirement here is we want to detect aircraft in the air accurately and in real time. Some of the challenges here are resilience to background noise. Many aircraft from different classes look similar. Example here, early warning aircraft look similar to commercial, and many aircraft within the same class look quite different. Example are all four of these fighters look very different. And then we're going to have issues detecting aircraft at different distances from the sensor that captures the images. So aircraft that appear far away or small, and aircraft that are really close to the detector are going to be quite big in the image. And then we also want real-time object detection, which usually requires more simple networks. Some of the current approaches here are the Trans-FDET. It's been designed specifically for aircraft detection. It uses the efficient det as a background network, and then it feeds the output of that to a transformer network for long-range dependencies of the feature map, and which is then fed to a BiFPN layer. They got a mean average precision of 86.6%, and they did not have any metrics on real-time performance. Yellow was another popular model here. It is one of the first models with real-time performance of a 45 Hertz frame rate. It frames object detection as a regression problem. It has a single pass for both predicting bounding boxes and classes. It's more likely to have a hard time detecting small objects, but it's less likely to predict false positives on the background. It also struggles to generalize objects in new and unusual aspect ratios. RCNN was another popular one. First it will extract 2,000 regions from an image, which are then fed to a CNN for feature extraction, then fed to SVM for object detection. Fortunately, this one takes a long time to train and does not have real-time performance, but fast RCNN and faster RCNN resolve the real-time performance issues. Single Shot Multibox Detector here uses a VGG16 as a base network. It can detect and classify objects in a single pass of the network. It discretizes the output space of the bounding boxes to a set of default boxes using different aspect ratios and scales. It is a more simplistic model since it eliminates proposal generation and feature resampling. It had a map of 74.3% on the VOC 2000 dataset with a real-time performance of almost 60 Hertz. So our proposed approach here is using an SSD network with a mobile net base network, which the base network here was chosen after experimentation. The SSD and mobile net both have great real-time performance, and SSD performs object detection and classification in a single pass, which is important to obtain our real-time performance goals. Dataset used here was MADI from Trans-FDET, and here you can see the network architecture here. This is the main architecture here, and then various points we tap into it and feed it to a CNN, and then non-maximum suppression to get the classes, class confidence, and the bounding boxes. So we experimented with different base networks here. We did use VGG16 because it was the original network used by SSD, Efficient Net, which was used by Trans-FDET, and Mobile Net version 2 because it is a quick network that has a small number of parameters with still maintaining good performance. Um, the results here is we found that MobileNet performed the best, had the best efficiency and the best accuracy, so therefore it was chosen. And we also chose not to use the pre-trained weights since we had better performance without them. We also varied the image size. Smaller images generally give better real-time performance but worse accuracy, and larger images generally better accuracy but worse real-time performance. Here our results were that we got 512 by 512 with the best training accuracy and pretty good efficiency for predictions. Therefore, we use 512 by 512 as the input image size. Data augmentation, we used it to artificially create more training data. We used change in hue, contrast, random lighting, random saturation, and flipping the images. Each augmentation has a 50% chance of being applied, and they can be stacked. And we found that all augmentation methods implemented gave us the best performance. We also varied the SSD loss function weight, and we found that the best parameter for this, best value for this parameter is 1. Because if we decrease from 1, our mean average precision came worse, and if we increased from 1, then both the mean average precision and the loss during training worsened. We also played around with the aspect ratios, and here's the aspect ratios that we were using, and we found that if only aspect ratios for long rectangle bounding boxes were omitted, then we couldn't detect the side, front, and backs profiles of aircraft. Likewise, if we got rid of the square aspect ratios, then we couldn't detect the top or bottom of the aircraft. So best case here was a variety of both, and then we varied the learning rate here, and then we found that 0.005 gave us the best performance. We also experimented with the match threshold and neutral threshold. Basically, anything above the match threshold is a match. Anything below the neutral threshold is a miss. Anything in between is just not counted. It's neither a miss nor a hit. And then we found that 0.75 and 0.5 gave us the best performance here. Optimizers here, we used Atom and SGD, since SGD was used by Efficidet, Efficidet. And we found that Atom gave us the best results. We also played around with the L2 regularization factor. Here, we chose a value of 0.005 as being the best, since it had the best accuracy here. So unfortunately, after training the model with all the best parameters, we were unable to get a good mean average precision. Here we did the worst on the fighters, most likely due to the variance or large variance in features on fighters. We did the best on helicopters and the second best on early warning, mostly because those aircraft had a less variance within their own classes. And then commercial and early warning didn't do so well because they were confused with each other a lot. And then here's some actual images with the predicted bounding boxes in red and true labels in green. And we see that we were mostly able to get the predicted bounding box onto, I'd say 80% of the aircraft. We had some weird corner cases where the aircraft would get, or the predicted bounding box would be grab the aircraft plus background noise. And we also saw that we did not do too good of a job at detecting smaller aircraft. Real-time performance here, we got a performance of 30 milliseconds, which equates to about 33 hertz frame rate. And it's possible to achieve better performance using better hardware. Here we only use a 3070 Ti. And here's just an image of the time it took to pass one image through the network. So conclusions here: we are okay at detecting most aircraft, at just detecting, not good at classifying aircraft, unfortunately. Worse was the fighters, best set with the helicopters, and confusion between commercial and early warning. We also had difficulty with farther away aircraft, most likely because MAD-EYE is skewed towards images where the aircraft is front and center. It does show promise when detecting helicopters and commercial planes. It is likely that if the network were to be trained and tested on just helicopters and or commercial planes, we'd have better performance. And then we are also successful at meeting the real-time performance goal. Okay, now I'm going to go ahead and do a code demonstration here. So it is important to note here that the training and test scripts do not take any input arguments on the command line. Instead, they take in a configuration file where you can give it the data set, the location, the hyperparameter values, and the classes here. And to run it, it's very simple. You just run the train script here, just simple in the environment, and this is assuming that you've already set up your environment using the environment YAML file. All these warning messages during training and information messages during training can be safely ignored. And it takes a minute for this to start up here. I'll just give it a second. Okay, so now you can see it's going to start training, and this will take probably around 2 to 3 hours to finish training. I'm just going to go ahead and cancel it. And then to run the test script, very similar, Python test.py, hit enter. It will load up the network. Again, the information and warning messages can be safely ignored. And then we can see it's just running through all the training images here. And I'm going to go ahead and cancel that because I don't need to run through it all again. And that concludes my code demonstration here. Oh, sorry, one more thing. The test script will print out the predictions in CSV files here. Here in this test predictions location, and then it will also give you annotated results here, where you can see the actual bounding boxes on top of the aircraft. And to note here, I am displaying all the bounding boxes that were predicted, even the worst ones. Generally, you can set the script to only draw the predicted bounding boxes that have a confidence of a certain value or higher. So this concludes my demonstration here. Thank you.